Okay. So yeah, today we're gonna talk about tensor products. Um, but before we go into tensor products, I will first explain how this, like why this object is such a natural thing to even think about in the first place. So we'll we'll look at two ways of defining tensor products mainly, and then um I'll give an exercise on the Discord um that gives a third more more abstract definition of the tensor product. Um, and you'll see how you'll if you do the exercise, it'll give you motivation for a lot of the things we'll talk about when we talk about category theory. Okay, so so let me just put down some base things. So today we're going to talk about finite dimensional vector spaces. Vector spaces over R. Okay. I'll make the restriction that we're talking over R. If I talk about vector spaces over other fields, I'll make that distinction clear when we talk about that. Okay. So before we jump into tensor products, let's look at the following vector space, right? So if I have a vector space, if V is a vector space, um, and I look at V star as being the set of all F from V to R, such that F is linear, this is called the dual space. Okay. The reason this is called the dual space is if we have vectors, if we have linear maps from V into W, if we have a linear map, right? Um, we then have a natural map going the other direction called the transpose um, of this linear map. Okay. And what it does is, what the transpose does is that the transpose acts on a function f. So f is now, f here is in the dual of w. And then the transpose applied to f is now in v dual. So its action on v, okay, is defined as TTRF of v is just equal to f of tv. Okay. So there's like a natural correspondence between um, matrices and between linear maps and then linear maps on the dual spaces, and this is sort of a natural correspondence, and that's why this is called the dual. Excuse me. In finite dimensions, yeah, in finite dimensions, V is isomorphic to its dual. Okay, but this isomorphism is but this isomorphism is not canonical. Canonical. Yeah. It depends on a choice of basis. So let's just give that isomorphism really quickly. So fix a basis, pick basis E1 up to En, okay, for V. Then define EI star, okay, in V star to be the linear map such that EI star EJ is equal to delta IJ. Okay. So this is called the Kronecker delta. Delta. And we'll be making use of this a lot. So what it is it's 1 if I equals j, and it's 0 if I doesn't equal j. Okay. And remember, we know that linear maps are uniquely determined by what they do on the basis. And since EJ is a basis, we know exactly what the map EI star is. Now the map EI to EI star is an isomorphism. It might be useful to think about why. So um, it's clearly injective. And it's surjective because, well, I guess the linear map defined as such. And it's surjective because if I take any component of, any vector in the dual, I can evaluate on the standard basis. And because I know exactly what my map does on the basis, I know exactly what the map is. So, so that's sort of the idea. Okay. So V and V star are isomorphic, but again, this isomorphism is not really canonical, and it depends on a choice of basis. So a lot of the times we now want to think of these spaces as sort of different, even though they're the same. In many applications, we'd want to like make a distinction between V and V star. However, it turns out that V is canonically isomorphic to the dual of the dual space. Is canonical. Okay. So if you take the dual space of the dual space, then V is canonically isomorphic to that space. To see this, consider the following map. So consider the map that takes V to the map EV at V. So what EV at V is now EV at V on some linear functional phi is just defined to be phi of V. Okay. So let's decipher what's happening. So you're going from V into V double dual. Okay. So it takes V, you're mapping V into EV of V. Another way of writing this is iota V. This is the one that this is what I'll actually use more. And now you take some element phi. If we try to decipher what phi is, phi takes an element in the dual space and it maps into R. Okay. And now you can take, and now remember phi is in V, so it makes sense to look at this composition. Okay, we can just take phi and evaluate it onto V. Again, you can check that this is an isomorphism, and it's a canonical isomorphism. And because it's a canonical isomorphism, from now on I'll identify V double dual with V. So from now on, if I write something like V of phi, this is actually equal to phi of V. Because phi is a map, V is a vector, but since V and the evaluation map at V are the same, same. Canonically, I'll use this abusive notation. Okay, is there any questions about this? Okay. Now that we have this, um, let's actually um, let's actually look at something very interesting. So now let's define the tensor product. Okay, so this is so we want to think of like um, we want to think of V star as a very natural space that corresponds to V. Um, and then now we want to like extract properties of V and V star and sort of, you know, get a better vector space. So um, so take vector spaces V and W. Again, I assume that they're finite dimensional, yada yada yada, whatever. Um, Actually, for now, we don't really need them to be finite dimensional. So for now, V and W may not be finite dimensional. So here, when we talked about it here, V was finite dimensional. For now, for the next couple of moments, V and W are not finite dimensional. Okay. So now what we can do is we can think of vectors in V and vectors as W as just formal symbols. Okay. Um, so let the free vector space over V and W be the space of all finite linear combinations, to be the space um, such that um, every element in V cross W is a basis element. Okay. What do I mean by this? So let's take an example. So let's say we want to take the free vector space um, over. I'll denote that as like f of r and r. Okay, so here this is f of v and w. So f of r and r. So what this is saying is now this is equal to the span um, of everything of the form a comma b, where a is in r and b is in r. Okay, so the vectors 1 1 is different, is linearly independent. And to the vector 2 comma 2. Okay, there's no relation between 1 1 and 2 2. Okay? In particular, 2 times 1 1 does not equal 2 2. Okay, so 2 times the vector 1 1 is a different vector altogether. Okay. Are there any questions that relate to the free vector space? Because I think this is a slightly confusing idea. Are there any questions? Okay. And now, oh, there's a question. Okay. Um, okay. With this out of the way, let's now. Okay, so now this vector space is huge, right? It took two finite dimensional vector spaces and gave us like an infinite dimensional vector space that's basically useless to us, right? It doesn't it's not a nice vector space to work with. So what we're gonna do is we're gonna impose some relations on the vector space, um, so that it reduces the dimensionality, hopefully. And it'll be relations that are like very useful to us. Okay. So firstly, what we're going to impose is now V tensor W is going to be defined as this free vector space V over W, and then we're going to quotient out certain relations. So what are these relations? So firstly, we're going to say that if I have V times lambda W, where lambda is a scalar, I want that this has to equal lambda VW. Okay, I need this. Secondly, I'm gonna say that, okay, if it's in the first entry, we also want to be able to take it out. Yeah. Another thing we want is that if V1 plus V2, we want this to be the same as V1W, V2W, right? So we should be able to break out the things. And then we want that if it happens in the second entry, then it's also okay. So V like this minus W1 minus VW2. Okay. So we want these relations on our vector space, on our free space. And now this gives us the tensor product um, between V and W. Okay. So so we can think of we can think of vectors in V tensor W as finite linear combinations of elements of the form V tensor W. Okay. But the tensor product is not okay, so it is technically symmetric up to isomorphism. But what we can do is if we have lambda of V tensor W, this is the same thing as lambda V tensor W. Um, but this is also the same thing as V tensor lambda W. Okay. Um, and also it's linear in each component. So if we have V1 plus V2 tensor W, this is the same thing as V1 tensor W plus V2 tensor W. And V W1 plus W2 is the same thing as V tensor W1 plus V tensor W2. Okay, so as we can see, these relations that we've imposed sort of make this tensoring operation into a bilinear operation. Okay. And the exercise that I'll give you regarding the tensor product says that it is the unique linear map that converts bilinear maps into linear ones. And I'll define everything more carefully on the exercise. Okay, are there any questions for this? Okay. Okay. Now let's do some examples. Let's do some examples. If you've done quantum mechanics, you know that if you have a multi-particle system, a general state is a tensor product of states, right? So in quantum mechanics, um, for multi-particle systems, a general state is a tensor product. Sorry, is a linear combination of tensor product states. So what do I mean by this? Say we have one particle, it can be either plus or minus, but then we have two particles possible. So this is the eigenbasis. Then two particles can be described as a, like I don't know if you've seen the notation. It's written like this, up to some normalization, of course. Um, so yeah, your general state vector is um, so your general state vector is something that like this, and the product here is nothing but the tensor product. Okay, so um, this sort of gives you entanglement in quantum systems. The fact that the tensor product may not always decompose gives you like that is the fundamental cause of entanglement from a mathematical point of view. Okay. Okay. So why are tensor products so useful in math, right? Because again, people study tensor products outside physics, but why are they useful? So usefulness. If I have two finite dimensional vector spaces, so if V and W are finite dimensional, okay, it turns out that we have a very nice isomorphism. Turns out the space V star tensor W is actually isomorphic to the space of linear maps from V to W. Okay. So let's talk through this one because I think that this one's a little um is a little out there, right? So let's talk about why this might be true. Um, oops. Okay. Remember the isomorphism we gave with the evaluation map, right? The evaluation map. So let's take some let's look at what how we can give a natural notion um to a natural action to this vector over here. So phi, so let phi be in V star and let W be in W. How can we give off like so now we claim that this thing has a natural action, has a natural action on V, right? That gives a vector in W. But we already have a vector in W over here. That's this vector over here, right? So we can define the action of this thing on V to be nothing but phi of V times W. Because remember, phi of V is in R or C or whatever field, and then we can multiply it by W, okay, to get a vector in V, sorry, in W. So doing it this way, we see that, okay, um, if you have a pure tensor product, you can define a natural action on vectors in V by just multiplying it by the dual part and then multiplying that into W. And then this, of course, like this action extends linearly, linearly to all of V star V dual tensor W. Right. So an arbitrary vector looks something like let's see. So we have a finite linear combination of so you have alpha I times phi I tensor W, right? This is what an arbitrary thing in V star tensor W looks like. And then we give it a vector in V, and all we do is, okay, we want this to be linear, so we extend everything linearly, and then we're left with phi I of V. So this should be a WI, and then this is WI. But this makes sense because this is just a member of your field F. You multiply it by WI, and then you just add all of them up together. So yeah, the action extends linearly. And now it's an exercise. Pick basis phi1 up to phi n of v star and w1 up to wm of w, and show that the map show that and construct an isomorphism v tensor w into this maps vw by this like action, by the action above. Okay. So yeah, tensor products for us, this is going to be the key property of tensor products that we want to use. Okay. It's that we can treat linear maps rather than as maps as tensor products of vectors. Okay. Um, and then we can sort of go back and forth between how we want to like treat certain maps. As we'll see later on, certain maps are good being left as maps, but we also like to talk about tensor products. Um, Whichever makes life easier at the moment will be the one that's used. Okay. Are there any questions regarding this? Are there any questions regarding the isomorphism that we defined, or how we define the tensor product? Because the tensor product is one of the most important things that we will define, um, because everything uses tensors from now on. Which isomorphism? Um, I mean, in finite dimensions, you can reduce the first isomorphism theorem to rank nullity. Um, so I like if you want to use first isomorphism, I feel like that's a bit of an overkill when you have rank nullity. Because a lot of the theorems just reduce down to rank nullity in finite dimensions. That's why it's sort of nice. Yeah. Okay. I mean, first isomorphism and rank nullity are basically the same, just in different settings, like slightly different settings. Okay. 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 So okay. Now we're going to define a very do you guys know what an algebra is? I think I like spoke about this like 2 classes ago.
Sorry, what?
What an algebra is over a vector space. I guess algebra over a field.
No.
Okay, so an algebra. Okay, let me just define it very quickly. Because we will use the notion of an algebra a lot. So an algebra um over R or C is a vector space. Um, is a vector space with a map. Um, I'm wondering how I wanna define this because there's a couple ways I feel like. Mm. Okay, so it's a I guess the way I need you guys to know is it's just a vector space with a multiplication. The multiplication need not be associate. Sorry, it must be associative. Um, associative, but it doesn't have to be. It doesn't have to be commutative, nor does it have to be unital. Um, but it has to be bilinear with a multiplication that's bilinear. I mean, bilinear just comes down to it being like distributive. So, um, okay, so let's do some like nice examples. If we take R3 with the cross product, okay, is an algebra over R. So you see, the cross product is not commutative, but it's anti-commutative. It's associative, but it's yeah, but it's not unital. There's no unit. Right? There's no element that I can multiply it by to get one, or like sorry, get itself. So this is like the main example. Okay. So what we can do now is we can define the following tensor product. So define V tensor n, okay, to be the space V tensor producted with itself n times. I'll also write this like this, like. Now you might ask me, oh, don't we need brackets to um, make sure that the tensor product, like making sure you're grouping the right things and then taking the tensor product in the right order. The order of tensor product doesn't really matter that much because it's associative. So taking the tensor product is associative. What I mean by that is V tensor U tensor W is isomorphic to V tensor U tensor W. Okay. And also V tensor W is isomorphic to W tensor V. Okay. Um, Again, I feel like the isomorphisms are pretty obvious once you know what you're looking for. Um, but yeah, if you want, you can check this. Okay. So yeah, so we define this tensor product. The way we want to think of this tensor product, right, is these sort of give you the homogeneous polynomials in n variables. Okay. Well, a lot more variables than n variables, but these behave like homogeneous polynomials. Okay. Um, so a homogeneous polynomial is just if you take p of lambda z, this gives you lambda to the n p z. Then p is homogeneous of degree n. Okay. And now what I'll do is I'll define something called the tensor algebra. This is the tensor algebra over V, and it's defined to be the direct sum as I goes from 0 to infinity of V tensor I. Okay. So what this sort of looks like is it's your field tensored with V, sorry, direct sum with V, and then direct sum with V tensor V, direct sum with V tensor V tensor V, direct sum, so on. Okay. Um, don't overthink this definition. Just think of it as a polynomial. Um, yeah, just think of it as like a polynomial. That's the best way to like make sense of this. Okay. Are there any questions regarding the definition of the tensor algebra? Okay. So now we can talk about like more algebras, okay, from the tensor algebra. So have you guys heard of the symmetrizer and the anti-symmetrizer in maybe quantum mechanics? That's
No,
where you
not
might have
yet.
heard of it. Okay, okay. Hmm. Okay, so then let me leave that for next week. We'll talk about so yeah, we'll talk about the exterior algebra and symmetric algebra. Um, if we have time after today. Okay, so just keep in mind the definition of the tensor algebra. This will come up again when we talk about differential forms. When we talk about spin, this will come up when we talk about spin. So this does have like some use. So for now, just keep this in the back of your head. And I guess we'll also discuss the Clifford algebra. Um, but the Clifford algebra requires a lot more structure on the. Okay, now let's talk about what we want. Like now, okay. Well, I've now said that like V tensor. So okay, this means that V tensor V is we can think of V tensor V as just the group of linear maps from V to V, right? From our thing above. Um, but how can we think about this tensor space? Okay, sure, it's the linear maps from V into V dual, right? But is there another way to think about this? Remember that V and V dual are isomorphic. So what we can do is if we take a map, so if T is a map from V into V dual, what we can do is we can define a map T hat that's bilinear, okay, um, and it goes from V cross V into bilinear, okay. So we can think of maps from V into V dual is bilinear maps from V cross V into R. And the action sort of, I mean, okay, first we have, if we take a vector V, we get something in V dual, so we have to give it a vector in W, right? Um, and how do I want to define this? I think this is how we define it. Okay, so it's going to be T, so this should be VW, and this is going to be TV of W, okay? And now you can check that this is bilinear. I mean, I think it's pretty obvious that it's bilinear because T is linear. Um, and then the V component is linear because it's a linear function. Okay. Um, okay. So yeah, we can think of bilinear maps as just tensor products. And then because of associativity and other things, right, of the tensor product, we can think of trilinear maps as tensor products. Okay. And then so on and so forth. So um, a multilinear map, um, V cross, yeah, V cross V cross V cross cross V into R can be thought of can be thought of as a member of V. So if I have n things here, I can just think of this as like V star dual tensor producted with n times. Okay. Oh, Okay, but this is all sort of a little abstract, right? Um, so let's make use of the fact that we're over finite dimensional vector space and take a basis EI of V. Okay. Then we get a corresponding basis. We get a basis EI star of V dual. Okay, but I don't want to keep writing EI star. So what I'll say is I'll denote E upper I. Okay, I'll denote E upper I by E star I. Okay. So if I have an up index, then it's a covector. So vectors in the dual space are also called covectors. Um, okay. So then this now tells me that a map, um, that a bilinear map T from V cross V into R is, so I can write it as the sum over I from 1 to n, sum over j from 1 to n of T. Okay, so now I have, so I'll write it a little funnily. I'll write it as T upper I and T lower j, Ti tensor T like ej. Okay, but okay, if I consider like more multilinear maps, writing down the sum again and again is gonna get really, really, really annoying. So what we do is we just write this as T upper I, T lower j, E I tensor E j. And then the convention we use is that if you have a lower index and it and you have the same index upstairs, you sum over them. Okay. So j is summed over. And then again, you can see here that I is up and I is also down. So you sum over I. Okay. So you sum over I, sum over j. This is called Einstein summation convention. So this is called Einstein summation convention. I will admit, initially it's going to be very hard to sort of keep track of what's happening, but over time, the more you use it, the more you'll see that it's actually very useful. Okay. So from now on, I will use Einstein summation convention. Um, yeah, I'll use Einstein summation convention. Um, I'll let you know when I'm not using Einstein summation convention. Um, okay. Are there any questions? Okay. So, okay, we've looked at these tensor products, but remember in the beginning, I mentioned that V and V double dual are canonically isomorphic. Um, so let's now use this isomorphism and then let's look at linear maps. Um, okay, see you, man. Bye-bye. Um, so let's look at linear maps like from V dual. Okay, and now we can okay, see ya. Okay, so using the isomorphism, so using V double dual is canonically isomorphic to V, we can look at multilinear maps over V star as members of V tensored with itself n times. Just using the same argument we had above. Um, well, I guess multilinear maps into R. Um, there is there is a notion of differential forms over that taken values over an arbitrary vector space, but we'll define them much later on if we even get there. Okay, so so now this tells us that the tensors, and now we'll see in physics that like these two types of tensors are enough to um, describe a lot of the physics that we want to study. Um, okay, so so um, so okay, we're gonna call so now we're gonna look at the general family of tensor spaces. So so in physics, the tensors we study, well, I guess the tensors we use, will be from the following space. Okay, so there isn't any good convention about this really, but I'll call this T with a like a fancy T, KL over V, and this is going to be nothing but um, V tensored with itself K times, and then it's going to be V dual tensored with itself L times. Okay, and then
I,
you.
I actually had a question. So I'm a little late showing up to this, but is there a reason why we write K like first and then L kind of beside it instead of along the same column?
Oh yeah, so that follows from just Einstein summation convention. So we I get tired of writing V star over and over again. So instead of denoting the star, I just raise the index.
Okay.
Um, I just raise the index like into an upstairs index, and then um, to make summation convention legal, I flip the convention in the coefficients. Um, so the coefficient of a vector will be upstairs, and the coefficient of a covector will be downstairs. I hope that does that answer your question?
Yeah, that's good.
Okay. So okay, let's continue now. So we call um T in this fancy T KL a tensor of type KL. Okay. This means maps from V to V are of type 1, 1. Okay. Uh, Dual vectors are of type 1, comma 0. Um, Double dual vectors or vectors are of type 0, comma 1. So this last thing follows from the um, from V being canonically isomorphic to V double dual. Okay. So now I want to just take some time to talk about transformation laws of tensors and why I think the way we study them in physics is a very bad way of introducing what the tensor is. I think this way of introducing a tensor is better, mainly because we know what linear means. So the notion of a tensor um, is quite canonical in the sense that it follows immediately from the constructions of linear maps. So we want to generalize linear maps, and the next best generalization of a linear map is a bilinear map, which, as we saw before, is just a tensor. Um, we saw it's a tensor of type 0, 2 as well from over here. So you can think of bilinear maps are of type um they're of type 2 0, 2. Okay. Okay, so now let's work in coordinates a little, and let me show you that the transformation rules that we see for tensors actually follow immediately um, from the notion from this general notion of a a general notion of a tensor product. So so we have we have basis EI of V and E up I of V star, and remember this is the corresponding dual basis. But now say we go from one basis. Now say we have another basis. Let me actually call this AI. This AI, and then let's say we have another basis BI of V, and corresponding dual basis BI of V star. Now we can have a change of basis from V into V that takes AI into the vector BI. Okay, this is a change of basis. And now my question is, okay, I know that my basis vectors change using T. So how does my dual basis change, right? So we want to figure out how does AI go to BI? So like what transformation takes AI into BI? If you remember above, we can write a map from V into V as V hat from V tensor V dual. So this means that T hat, I'll be less, I'll be a little loose with it and call the map T hat and T by the same letter. And then I can write this as Tij, um, AI tensor AJ. Okay. Moreover, what this tells me is that this tells me that BI lower is nothing but T J I A AJ. Do we follow so far?
Yep.
Okay. Sorry, I also misspoke here. We want to figure out um how does the components of a vector in basis AI transform to basis BI. Okay. So we can now write BI as TJI AJ. And now say we have a vector equal to VIAI. Okay. Um, but then I know that this has some dual, like some other coefficients for the BI coefficients, right? So, but I know what BI is, okay? So I know what BI is in terms of AI, so I can just substitute that in. Okay? So T J I A J. But now the coefficients in a basis are unique, right? Um, so what this tells me now is that so the corresponding coefficient of AJ is this is this um, is this coefficient over here. So this tells me that VJ is nothing but VI TJI. But this isn't what we wanted. We wanted how does the coefficients V squiggle relate to V, but we have a relationship going the other way around, right? So what we can do is we can um multiply this matrix. Sorry, this we can multiply this expression by the inverse matrix of T. Okay, we can multiply by the inverse matrix. So we can multiply by. So now this tells me that. Um, so if I call the inverse matrix A of A, um, and then it has coefficients. I don't know. Let's just call it AI. Um, JVJ equals this I. Uh, let's actually multiply this by K here. Okay. And now since T and A are inverse matrices, this is just matrix multiplication. So this ends us with delta JK. Okay. Delta JK. Um, do I want, sorry, wait, I messed something up. So if I have I can make this J, and then I make, oh yeah, this becomes this becomes J. Okay, and now this is just delta JJ, which is just one. So what I'm left with is, um, so the components of V transform um, by the inverse matrix. Okay. So that's interesting. We sort of have a dual relationship between vectors and their components. Right. So if a vector transforms in one direction, the components transform in the other direction. And that sort of makes sense because you want um, that makes sense because you want the components, like the component transformation, along with the vector transformation to cancel out. And the only way they can cancel out is if they're inverses of each other. Okay. Does that make sense? Are we happy with this? Okay. Now, um, now let's see how the dual basis transforms. Okay. How does the dual basis transform? And we do in like a we pretty much do the exact same thing. So say that let's say that bi is now equal to Cij um, aj for some transformation where Cij is some transformation. Um, so I mean we technically have to write this as Ij because the order swap. Um, but we can afford to not be that stringent just yet. Some transformation V dual into V dual. Um, and now we can use the definition of the dual basis to sort of um, help us figure out what this does. So we know that delta ij is nothing but bi applied to bj. Right? That's the definition of the dual. And now we know that we know exactly how bi and bj transform. So we can replace bi. So we have Cij a upper I, sorry, a upper j, and then the bi's transform. If we look above, they transform as where did it go? They transform as this. So we have t k j um a a k. Okay. Oh wait, I have an upper and lower index. Oh, this should be an I. Okay. Also, I messed that up here. This should be a J. This should be an I. This should be a J. Actually, I have to use another index. So this has to be a K. This is an I. This is a K. And then BJ. So I need a J there. So this is L. So these are L's. Okay. Sorry about that. Okay. And now the map AK is linear, so we can just pull everything out. So we have CKI, DLJ, AKAL. AKAL is just delta KL. And now we can just set K equals to L. So KI T. So this L can become a K. A, A, K. And what this tells us is that CKI is the inverse matrix of TKJ. Well, matrix, right? Because this equals delta IJ. So the covectors are now transforming by the inverse. And remember, we already know now how the components of the covector must transform. They must transform as the inverse of the inverse transformation. So they transform by the transformation itself. Okay. Now, if I defined a vector or a covector as an object that transformed under this way, I feel like that's a bit confusing on its own. But when we define the tensor product as like these bilinear, as a bilinear product on vector spaces, the transformation law just pops out. So in classical mechanics, we call vectors, the things we call vectors are a collection of numbers that transforms this way under a rotation, like a specific rotation matrix. Okay, um, so yeah. And then we define tensors as just higher degree analogs. So we will see the transformation law for a general KL tensor now. But are there any questions? There no? Okay. So now take a general um, tensor. Let me turn on the light in my room. One second. Okay. So if we take a general tensor T from KL, okay, we can define, um, I mean, not define, we have the following decomposition, right? We have T equals a slew of indices now. So we have Ti1 up to Tik, um, J1 up to Jk of EI1 tensor all the way up to EIK tensor E J1 tensor E JL. Okay. So instead of writing all of this, we can talk about a tensor just by its components. So we don't have to um, write out all this every single time. But now we know, um, and now we take a transformation A that takes the basis EI to the basis E prime I. Okay. Doing this, we can now we can now first see um how do the dual sorry how do the tensor base how does the tensor basis transform? Okay. So how does this object transform? How does EI1 tensor EIK tensor EJ1 tensor EJL transform? And the best way to do it is just write it out. Okay. So E um so EI1 prime tensor E prime IK tensor E prime J1 tensor EJL. Okay. This is the same thing as, okay, so I know that EI1 is nothing but A M1 I1 EM1 tensored with AMK IK EIK tensored with, and now I know that the dual basis transforms by the dual matrix. Sorry, the
Why
inverse.
is
Yeah.
it that in like just above it's tensor EJL instead of E prime? Is that like
Oh, that's a typo.
okay?
Thank you. Okay. Thank you for that. So okay, then here I know that this has to transform by the inverse matrix. So this is a inverse of J1 N1 E um, EN1 answered and all the way up to. Also, we know that so we can write the inverse matrix by just swapping the components and then putting the up index into a down index. But we don't really need to do that right now. That's just one thing we can do. Um, and L E and L. Okay. And now using the multilinearity of the tensors, we can just bring all the factors out front. Okay, so we have A M1 I1 dot 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 A M K I K A inverse of J1 N1 dot 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 A inverse JL NL EM1 tensor E. Sorry, this should be lower. This should be MK. Sorry, MK tensor EN1 up to ENL. Okay, and now all we really have to do. Okay, so we could just leave it here and say, okay, we're happy because we know we argued above that. Um, we sort of require we require that we factor out say we cancel out this term, right, under the transformation. So the components must now transform by the inverse of these. Okay. Now components, but we can write that out more. Okay, so components must transform by the inverse. And we can see this as follows, right? So if I write T as T prime I1 up to I k, J1 up to Jk of this, like times this thing, okay? I can just replace this thing by this expression over here. So let's do that. So I can replace it by this expression. And then I'm multiplying out front by T prime I1 dot dot Ik J1 Jk. Okay. So this should be JL. I'm not sure how that became a JK. JL. But again, this thing forms a basis, right? So the components are unique. Hence, the component tm1 up to tmk, n1 up to nk must equal this monstrosity over here, right? And now we do the same thing we did above, right? Where we just multiply by the inverse matrix every time and then cancel everything out. So what we end up with is that T prime I1 up to IK, J1 up to JL. Now I need A inverse of I1 M1 for this matrix. And then I do the same thing, and now I need an inverse for this matrix. So this is IKMK. And then I need the inverse of this matrix, but that's just the matrix A. So this is a N1, J1, so on. And I'm left with NL, JL. Um, Times T of M1 up to MK, J1 up to JL. Okay. Does that make sense? Sorry, this should be N1, not J's. These are N's. Okay. So now, okay, we can also see the usefulness of Einstein's summation convention, because if I had to write K plus L sum signs, I don't think I could fit anything in one line. Okay. So so the transformation laws for tensors follow very quickly from the transformation laws of um like just from the definition of a tensor. And so I think it's better to see the general case of a tensor, and then we can specialize and say, okay, in physics, we require tensors transform under this way by rotation matrices. In special relativity, we'll want Lorentz transformations, right? In so, for example, in like in early relativistic quantum mechanics, um, your wave functions transform under a certain spin representation, which is just nothing but a tensor, but it's I feel like it's more complicated when you define something by how it transforms rather than what the object actually is. Um, okay, so are there any other questions regarding what tensors are, what um, and what like how they transform and other such things? And the many isomorphisms between tensors and linear maps. That's another. Okay. With this now, I will give motivation for next meeting. Um, so is the idea is that the determinant um, tells you tells you the hyper area of the parallelogram. Well, I guess it's called a paralleloid or something like that, but I'll just call it a parallelogram spanned by some basis by E1 up to En, where this is a basis after the transformation. Okay. So what I mean by this transformation. So what that means is, for example, we have before the linear transformation. So this is E1, this is E2. So the parallelogram span is this. Okay? And now let's say we transform it, and it transforms into something like that. So the parallelogram spanned by it is this thing. And this new area is called the determinant of T. Okay. Okay, it's not really the area, it's more so the signed area. Um, yeah. Because remember, determinants can be negative, so we have to somehow interpret that. Yeah, so it's a signed area, so it sort of gives us a notion of orientation. Okay. Gives us a notion of orientation. So, okay, the determinant does a couple things. One, it gives us areas, so it's useful when we want to integrate. And it gives us a notion of an orientation, which is useful when we want to define things like the cross product or the right-hand rule or the endless number of things in physics that require the notion of an orientation. Okay. Another property of the determinant, right? Another property is that the determinant is multilinear in the columns of a matrix, right? So um, if I scale a column in my matrix, I scale the entire determinant by that same factor. If I add one column, if I add a vector to one column, I can split up the determinant and look at the original determinant plus this new determinant. Okay, so it's multilinear, but we just developed so many tools to talk about multilinear maps. So what this tells me is that the determinant function is actually a tensor, um, is actually a tensor. And what it does is it takes in vectors and gives me a number. Um, and so it's of type 0 n. Yeah. Um, Here n is the dimension. Okay. So the determinant is like this special map. Moreover, the other property of the determinant is that it's alternating. Is alternating. And what I mean by alternating is that if I swap two columns, I pick up a minus sign, right? And this sort of makes sense because now I've flipped the orientation. So my area is flipped up to a sign. Right? And um, as it'll turn out when we talk about the exterior algebra, that being a tensor of type n, like 0n, um, and being alternating puts you in a one-dimensional vector space. Okay. So every alternating multilinear map is a scalar multiple of the determinant. Okay. So So this sort of gives us motivation to look at maps that behave like the determinant, because the determinant has the like properties of orientation and area, right? Those are very important to us. So that's what the exterior algebra hopes to generalize, and that's what we'll talk about next meeting. Are there any questions? Okay, then I'll end the meeting here.